Okay, I got that. Okay, welcome everybody to the second module in the grad course Tame Phenomena over the real field. I don't know if people have mentioned this so far, but we have set up some informal resource pages for people to go get information or for lecturers to post things where we can just stick stuff up and not worry about what they look like. There's a resource page for the main program that is right here. It's a Google site or whatever it is, Google something. And there's a particular resource page for this module that can be accessed either through this page or just directly through this link. And one of the kinds of things that I posted on mine here are, for example, PDFs of papers that appear in conference proceedings that have never been published online anywhere, as far as we know. But these are we need to use these things from time to time. So that's the kind of things that you'll find there, or updates to things, or various remarks. So it's a good resource. So I'm going to start off by, oh yes, my preferences in this endeavor. This is a grad course, so I do request that the audience behave as though we're a normal pre-pandemic in-person graduate course, even when we are using Zoom. I don't monitor chat buttons. I don't do any of these kinds of things. I will not even be seeing any of that stuff once I get started. Attendees who are not graduate students are certainly welcome to attend as guests. That's the longstanding field's policy, but please remain aware it is actually a graduate course intended for enrolled students. So let's not turn this into a working seminar for professionals. If there's any students, in addition to any of the scheduled question sessions, I should say potentially available depending on the time by appointment. So if you ever want to talk to me just directly about any of this stuff, just to email me, or once the Institute gets hopping again, you can just look for me. All right, let's see if this thing can go away for a bit. There. Okay, so I'm going to start by reviewing a little bit of the part of my intro talk that I did in the workshop, because that'll help us reset things a bit. So here's my conventions for the moment. To start off with, a vector field is just a map from some subset of Rn into Rn, no other assumptions yet. A solution of F is just a differentiable curve or arc, if you like, on some infinite connected interval. That means it's an interval of some sort, except it's not a point. And we want to satisfy the usual kind of differential equation here. And my use of the word trajectory is going to be the image of a solution. Now, I mentioned probably in the introductory workshop that these two are fairly standard, although this one usually comes with more strings attached on it. But trajectory is used in a lot of different ways by a lot of different authors. So this is mine, though. It's really just, it's the trace, if you will, of a solution. So we know these pictures from undergraduate ODE theory. We think of a vector field as, you have a bunch of arrows coming out of points, and then a solution curve is the kind of thing that just goes through it. That would be that has the tangent, the arrows are the tangents of the curve as you pass through, and the trajectory would be the resulting geometric object. I know there's solution curves, streamlines, flow lines, whatever, they're all going to be the same. I just prefer to use trajectory. So I'll recall these motivating but ill-posed questions. What should it mean for a collection of vector fields to be tame, or mutually well-behaved, or natural, or whatever other kinds of things you want to throw out? Similarly, for collections of trajectories of vector fields, And similarly for collections of pairs of trajectories gamma of vector fields F. These are the objects that get studied in, well, at least what's called differential geometric control theory. I started getting interested in this, I think maybe when I was still in grad school, but I read a paper by this Robert Hart in some conference proceeding, I think from the mid or early 80s, and I was really fascinated by a lot of the stuff that was going on there. So I've always had some of this going in the background. So we're going to try to nail some of it down here in the next few sessions. But so of course this is all tap dancing around what's tameness and what isn't, and all these other things. So we'll make the usual things here. If you're familiar with first order logic, we have some by now routine conventions. We'll use definable is going to mean definable with parameters. I say mostly for convenience, but frankly, it's entirely for convenience. I think definable should mean definable without parameters, but I'm on the losing side of that for now. We'll denote the real field as a semantic object, not a syntactic object, with just an R, blackboard R with an overline over it. And I'm going to use this math tractor to denote an expansion in the sense of definability of the real field. If you're not familiar with first order logic, I know this has been run by several times already by this program, but we might as well do it again. We look at this and we basically identify, we take a structure in the logic sense and then identify that with the collection of its definable sets. So what we get from that, we can say we have a sequence of Boolean algebras. These are subalgebras of each Rm, so that we are sort of closed under an obvious upward boosting operation, closed under projection on the first M coordinates, and these zero sets of all real polynomials are there. Those are the minimum requirements. And so now definable in the structure R is simply the same thing as saying it's a member of some Rm. And we also always have to remember definability is always with respect to some given structure. It does not make sense to talk about definability if we haven't nailed down or said this is the arena in which we're going to be working. All right, so here's basically what we're going to be looking at. We have some collection of trajectories of definable in R vector fields. And the game is going to be, what can we say relative to the base structure, what we started with, about the expansion when we add these trajectories in. So if for the non-logicians, this is simply, this would be the notation for the smallest structure generated that has all the definable sets of R and all of these trajectories in it. All right, so again, if every trajectory is already definable downstairs, then trivially we win. That's of course not very interesting at all. So it does get interesting sometimes. We might not actually know which trajectories are definable and which aren't, but generally we're going to be looking for new things to put on top of what we started with. Now, this is one of these facts that gets used all the time in our subject. An expansion of the real field defines all trajectories of any possible vector fields, if and only if it defines the set of integers. I've had mathematical friends ask me to explain how this works, and I've had discussions with some senior experienced high-level model theorists, and we all agree that this cannot be explained to anyone who hasn't at least gone through the proof of Gödel's theorem in a careful way. that's basically that. This is a logic thing, and you can't kind of explain it by these finite things of unions and projections very well. I was hoping actually that we would get a descriptive set theorist to show up at the program sometime and maybe give a little lecture on why it's true. It's an exercise in Kekris's book. All right, so if our base structure defines the integers, then again, trivially we win. Why? Because all trajectories are already there, so we can't add any more new ones. So there's nothing there. If we started with something that's at least not bad, if we started with something that avoids z, but then we add some stuff and we do get the integers, then okay, we might say we've won an instance of the game, but it's a Pyrrhic victory at best. What we know for sure is that we started with something that maybe we understood and had a chance of dealing with, and we wound up with something that, at least in terms of model theory or definability theory, we have no chance of dealing with. So that's really, neither of these are where we really want to be. So we're usually going to assume that the base structure avoids defining the integers, and we want to really try to rule out the collections of trajectories that will wind up defining the integers. And so that's a big part of the game. Now, on the way to doing these kinds of things, these kinds of questions come up. So what does the assumption of non-definability of the integers imply about the vector fields of R? What else should we assume about the base structure R? And I actually use these corny emphasis here, and why? Why should we make extra assumptions on things? This is going. Many of you know I have something of a amateur foundational bent in me, and these are the kinds of things I want to know. Why am I making assumptions? Why am I bothering to do things? So we'll try to talk some about these kinds of things. What else should we assume about the trajectories we consider? It's well known if you've had, say, a good advanced undergrad ODE theory course, that there are some trajectories in the world that are not what we have in mind. So we'll want to but come up again for reasons why we are going to focus on things and rule others out. What else should we assume about the vector fields we consider? In most of the literature that I run across, vector fields are nearly always assumed to be C1. But most of the time, the only thing you really need is locally Lipschitz. So I like to sort of try to keep track of this kind of stuff. So I'm not making technical assumptions until I'm forced to do so. That's the position. So now let's recall that our structure is O-minimal if every definable set has only finitely many connected components. Now, my first goal in this module is to try to convince you and us, or me, that we should play the game only over O-minimal base structures R. Now, for some people, this is not a problem, because O-minimal structures are, O-minimality is a very strong property, and it kind of makes it fairly easy to prove things about it. So it might just seem, well, and I don't know anything, I don't know of anything interesting besides O-minimality, so it's fine with me if we just stay there. But I'd like to find reasons for why we shouldn't consider other things. Along with this, there's some, actually, this will be the first thing. There's some other things that that we're going to, other conditions that we'll put on our base structure R that are sort of common, but if you hang around with ODE theorists for a while, or qualitative ODE theory people, you sort of you pick up this thing that, okay, we don't want to deal with things that are like are infinitely flat singularities or infinitely oscillating behavior near singularities, and or even frankly irrational power growth is a little bit shady. I mean, things should have things should not be too far away from behaving like real analytic vector fields. So one of my goals is to try to nail this stuff down a little bit precisely and say, well, there are actually reasons. There are reasons why we can say these things just besides our maybe likes and dislikes. So this is going to be the first goal. It's a modest one, and this will be what I'm going to try to convince you of today. I can't do all the details today, but I can tell the basic story. Okay, now comes the scary part. So I'm going to close this and switch to something else. Okay, that's fine. And now I have to do this again. Oops. Give me a second. Oh, now it's confusing me again. Ah, okay. I think we're there. Okay, I better test this though.
We don't see your share screen.
Ah, you do not?
No,
What do you see?
you.
Oh, all right, let's see. All right, we'll try again. Oh. The button got away from me.
Now it works.
Yeah, okay. Yeah, it's a sequence that I'm not really well familiar with. And I do want to get rid of these floating controls because they bug me. Okay. Okay. So basically, what we want to start off with a topological definition. So if X is a topological space, then a subset is constructible if it is a Boolean combination of open sets. Okay, so there's you might and let's say I might as well, I'm here, and for those set is locally closed. If it is the difference of two open sets. So that's equivalent to just saying you're the intersection of an open set and a closed set. And it's routine to check that you're constructible if and only if finite union of locally closed. And I'm going to go to abbreviations already, locally closed. Now, what we're going to be doing here is concentrating on expansions of the field of reals by constructible sets. Because if we were to really be, some of you might be thinking, well, wait a minute, if my base structure is not minimal, and by definition, it defines something with infinitely many connected components. So there have to be some kind of ridiculous vector fields that no one would ever look at that are living there. And that's true, but it doesn't necessarily mean that you'll get any new continuous vector fields. Right, so because you can add dense codense junk to a no minimal structure, and sometimes they won't see it, and so you actually don't change your constructible sets at all. So we're going to be looking at expansions. So we're going to look at expansions of our base structure we could even just do this, expansions of this guy by constructible sets of reals in any, in various Rn. Okay, so let's, for the moment, let's go ahead and let R be such a thing. Okay. And this is my sort of the pseudo the statement. This is the easiest way for me to put it. So let's also suppose that R is not O-minimal. Then it defines what I'm going to call a sloppy sine function. So what do I mean by this? The picture, I'm going to prefer to draw a picture to this. So let's get a little more room. So I should be doing something like this. And this is going to be 0. Oops. And this is stretching out to infinity here or whatever. And what we know is what this thing does. It goes in this direction, but it oscillates at least above and below the +1. We might stop actually. We might just go only that far, and we might come down one loop and stop here. But you go at least this much. So what we're saying is that this is going to be an infinitely oscillating function, and it has at least a certain amount of change in amplitude on each. It's not periodic at all necessarily. And this is the kind of picture that we're going to get. And moreover, we can take this thing to be CP for any given P in N. All right, so now we definitely are, if we're not O-minimal, we're going to get some monster like this. And now we're definitely going to get some new C1, C2, whatever, C100 vector fields. So, and now what could we do with a thing like this? So I hope the picture is good enough in people's minds. Now, okay, so leaving aside definability theory and all these other things, when you go looking in ODE theory, there's very little, there's really not much about infinitely oscillating functions that show up. And there's a subject called flow K theory, which is very, very, very specialized. But once we have this sloppy sine function, then of course we can do something nasty with it. So let's say let FRR be such a thing. and as CP as we want. Maybe just, we can't go all the way to infinity unless we have a flat function around or something, but as we can always go as CP as we want. And so then we, of course, we're also going to have the function f, or say t maps to f of 1 over t from 0 infinity to r. All right, so in the back of your mind, you should be thinking of this as, okay, no, I'm really looking at sine of 1 over t. Now, even in the few cases where something like this might come up, we've got this, we've got polynomials, we've got rational functions. The idea of trying to have a theory that deals with arbitrary vector fields where you're allowed to say, start looking at sine of 1 over some polynomial or rational function, then combine them over and over again into more and more complicated nested things like this, they're really, you can't really analyze these things, and they don't really show up anywhere in control theory. As I say, there could always be an exception to a rule, but these wouldn't necessarily be periodic in any sort of way whatsoever. They can be, and then of course their derivatives as CP as we want, then the derivatives would all have to be there as well. And so all of these, if we wanted to have a program where we say we're going to try to investigate the definable vector fields, well, we're certainly going to be forced to be looking at all of these things. And my position is that until we see a good reason to look at things like that, then we probably shouldn't. And you know, if we could play around with these things and come up with some real monsters and maybe have some fun with that, but that's not, we actually, so I essentially contend that this argument in a way validates what you know, some of my ODE friends, what their gut reaction anyway would be to no, we don't look at vector fields that, you know, that go oscillate infinitely often near the origin and things like this. This is not, you don't look at stuff like this in vector field theory. So if we believe that, then as soon as we have a non-minimal expansion of the field of reals by constructible sets, these things, and worse, believe me, much worse, are going to be there, and they'll still be smooth objects. So this is my sort of argument for why we really, if we're going to start programs where we systematically look at base structures that we believe are nice, and we try to adjoin trajectories of definable vector fields, then either we're going to have to be very careful about which vector fields we want to do this with, and then maybe it's not the program anymore, and then even decide which trajectories we want to look at, when in fact the better thing to do might be to say, well, okay, no, this really is an argument that we should stick to O minimality as the base structure in this kind of affair. And I so far haven't met anyone who disagrees with this position. I just find it satisfying that we can come up with something at least this concrete that verifies why we wouldn't want to do this. I mean, I should also point out that these sloppy, this you'd have to really dig into the calculus details of this, but these sloppy sine functions are locally semi-algebraic. In fact, they're locally polynomial even. They're constructed piecewise on using polynomials instead of bump functions. And so if you look at any finite piece of it, you're actually just looking at a semi-algebraic object. So any local stuff that you're going to look at that doesn't necessarily try to ruin your life by doing things like this, it's going to be fine. Then you're going to be doing semi-algebraic vector field theory again, near something. Okay, so these are weird objects, but they're not that strange. And so in closing for this one, my contention is that yes, we should really focus on starting with O-minimal expansions of the field of reals and start solving vector fields over them and adjoining trajectories. Are there any questions or comments at this point? Okay. So how do I get this sloppy sine function, by the way? It's not, there actually is a little bit of work that goes in here. I'm going to basically just sketch some of the construction. There are a lot of details. But one of the things this starts off with is a fun little fact about, well, definable topologies in general. I'll state it just over the reals, but if in any expansion of the real line, there's no algebraic structure there, but or there could be, but we're not requiring. In any expansion of the real line, constructible definable sets are Boolean combinations of open definable sets. Right, so this is a nice little thing to have handy. So if we unpack this, what we're really saying is that definable Boolean combinations of open sets are Boolean combinations of open definable sets, of definable open sets. So you get to move the definable around. This actually does take a little bit of thought, and there's an interesting story behind all of this stuff, but which I don't want to spend too much time on history or something, but it led one of my colleagues, now retired at Ohio State, to say, he said, this was the kind of thing that probably every undergraduate student of Hausdorff knew how to do, but now nobody knows how to do. So this is a step one here. So when we're working with expansions by constructible sets, we're really working with expansions by open sets, and that's an important little reduction here. So then this was a theorem of this was like my first theorem with Patrick. We were at Fields in '97. Up on the third floor. So if R is an expansion by open sets, then it is O-minimal if and only if every definable discrete set is finite. One direction there is trivial. Okay, so what we've got now, if we assume that our structure R that we're back at, except this is okay, if it happened to be this, but we've got our R, and if we're assuming it's an expansion by constructible sets and it's not O-minimal, then it defines an infinite discrete set. Not just something with infinitely many connected components. So we have to get an infinite discrete set there. Well, now we knew about that. You can already cause a great deal of trouble just knowing this, but we like to really, I want to really get these sloppy sine functions because we know they are a source of trouble qualitatively. Whoop. What's that? Scroll page. Huh. I have no idea what happened. What's this? Well, okay, we'll put that aside. Whatever that was, that jumped to a test panel from earlier. I have no idea how that happened. All right, so now we've got R here now, and it's an expansion of R bar, and defines an infinite discrete set. Okay, now the set of midpoints of the complementary intervals of the Cantor set are an infinite discrete set. And there's lots of infinite discrete sets that we can't quite do what we want with that. But in fact, more is true. And this was worked out by various people, including one of my former students. But it didn't seem worth publishing because it was too easy, at least in this form. We get an infinite discrete closed set. Well, and of course, now that we have, if you want to think of it, I've got an infinite discrete closed set. If I wanted to, I could reflect this either way around 0 or whatever. And now I've got, if nothing else, I have something that's topologically a lot like the integers. So they're separated and there's no limit points and everything. So you have a closed set. But in order to get our sloppy sine function, we want a little bit more. I think some people call it uniformly discrete or something. I guess I could put it that. Well, no, we also want that for all x, y, let's give this guy a name. For all x, y, and e, if x is not equal to y, then they're at least 1 apart, or some constant. So we also want to get this. Now, I will do some more details of some of these things in the longer class sessions, and I would encourage some of the grad students to think about, particularly, how would you get from here to here? Because the result with Patrick has to be black boxed. But the argument of going from here, of this one, to going from infinite discrete to getting infinite discrete closed, that's actually quite manageable. You just have to think about how to do it. And then similarly, for getting this uniform separation, that takes a little bit more thought, but that can be also dug out of some papers of Philip Hieronymi when necessary. So now what we have, let's start, we start to get a picture that we want here. All right, so we're starting, we don't know that they really are that well separated, but okay, we can pretend they are. We know they're all at least 1 apart. So now one thing we already know about this, so here's our E is going to be our definable infinite discrete set. And closed, and closed. Now some Adapat Tamrong Tanyalak and I proved this is eminently believable. But when you have this picture and your infinite discrete n closed, you can just go through. There's definitely going for any p, for any finite order of differentiability you want to give me. There's going to be, piecewise polynomial bump functions that give me exactly the zero set. This thing. And if the thing is, though, is that if they happen to be too close together, then you'd get smaller bumps. And this is just plain calculus. It's this function we would get here, it's going to have the zero sets. E is going to be exactly the set of zeros. And it's going to be definable. All you need from that, and with no other assumptions whatsoever, you can define one of these things just from E and the field structure. And it's really just a real analysis or calculus operation. So now what we've got is this infinite discrete closed thing. It's going off in either directions if we wanted it to. It doesn't have to. It can just be unbounded above. And we start just making it the zero set of some nice CP function that's actually locally polynomial or locally semi-algebraic for sure. And now again, this already causes enough trouble if you wanted to start playing around with, look at the vector fields you could make from something like this. But because we took this uniform separation kind of thing, the construction of the function gives me this, gives me that it might not be 0 or 1. Oh, wait, I should leave this like this. Now I'm getting shaky. I know that I can always get it to go above something. There will be a delta bigger than 0 that works, that we're always in between successive zeros. We will pop up above that value. We might stay at it, but we'll always get above it. Well, okay, so now it's easy just to hit it with a linear thing and go ahead and say it's 2. So now we'll say we have at least that much oscillation. And then of course we just shift it down by 1. And then we get our sloppy sine function. So we cut it right through the middle. And that's how we get this oddball function. So all the details in here are there. It's calculus and basic definability tricks, but these are rather monstrous little things, and I think it really kind of puts to bed the rest that there's no point in having a program where you look at an expansion of the real field by constructible sets, by constructible trajectories of nice vector fields or whatever. There's just no point in trying to do this as a general program, because these guys are always going to be there, and they're going to force the existence of an awful lot of crazy stuff that's not useful. So that's the flavor. I know I went through that a little bit quick, and we will do more of the details of some of these things on Friday, but I wanted to get the flavor of how some of this stuff is going to go on. I mean, this is a little bit like Church's thesis or something, though. Well, you can't prove that you have to stay with a no minimal base structure. That's fair enough. It's still at some point we make these decisions that the mathematical objects that are starting to show up are just too ridiculous to warrant a general theory. And I can't, if that's as far as I can get it to go now, but we'll be doing a little bit of that stuff before we start doing any application, any connection to hardcore ODE theory. So I think I would like to stop there. And let me try to close out of here and turn the Zoom back on. Okay, hey, that worked okay. And there I am.
Thank you, Chris.
Oh, right. So this is a class. Yeah. So, and it's the end of the day. I mean, I suppose I could entertain a short question, but I guess I gather the policy is that we don't drag this out too late, because I would be particularly interested in entertaining questions from grad students. But if they don't want to do it now, they could always email me. And anyway, we'll see more details on Friday.
You.
Cool enough?
I-
Very good.
I stopped the recording.
Yep. Okay. Bye. See you later.